Hi, welcome back for our asynchronous lecture, chapter 2, part 2 on fluid and physical properties. So previously we have seen three important physical properties of fluid. Okay, today we will see another three, so which completes the chapter. Okay, for chapter 2. Okay, so first we will see application of viscosity measurement. So initially in the third properties we have seen about viscosity. So there are some devices used to measure the viscosity level in the fluid. So it can be in the air or also it can be in the liquid. Okay, so we have a certain kind of arrangement. We call it a rotating viscometer. Okay, so this viscometer can be used to measure viscosity of the material. Okay, it practically as a setup, something like you can see here. So you have a rotating drum, you have a motor meter, you have a drive motor, then you have a fluid inside, and you have a stationary cup to hold the liquid. So this is a physical unit, the commercially available viscometer. So practically, it will start to rotate. The rotating drum will start to rotate, and based on the viscosity of the material, it will create some kind like a resistance, which can be measured by the viscometer. Yeah. So these are the calculations involved. Some of the formulas that you can use. So these formulas, some you already seen in the previous lecture, and some of the formula you can use here, like tangential velocity v equals to omega r, angular velocity omega equals to 2 pi, and wetted area a. Okay, wetted meaning so it's a connected area. Okay, so area is 2 pi rl for a cylinder. Okay, then you can calculate the top, okay, using all this formula. Okay, so we don't have much calculation so related to this, but along the way in chapter 3 and chapter 4 we will look at more practical calculations related to this. So without wasting our time, we will enter to the fourth properties, okay, physical properties of fluid. Fourth will be something that we call as surface tension. So you can see here the surface tension and the capillary effect. So you can see this example, water droplet. So these are something that we always see in a natural environment. So especially after rainy days or on the surface of in your house, in your surrounding. So you can see all these elements like a water droplet. Okay, so the examples are water droplets from rain hang on branch or leaves of trees. So something like this or something like this. So we can always see this. And water slider stay atop of a liquid and paper clip. Okay, if you don't break the surface tension of a liquid, so you can make certain materials or properties to float. Okay, something like paper clip. So even the razor that you are using in your house, so you can make it float. Okay, because the surface tension will not allow it to go further inside. Okay, so that's what we call as surface tension. So you will see some information about surface tension and also capillary effect. Okay, so you can see here. Okay, although all molecules are in constant motion, yeah, all molecules inside the liquid in a constant motion. A molecule within the body of the liquid, on average, attracts equally in all directions by all molecules surrounding it. Okay, so we will go line by line. So we can see the image here. So inside, so practically from this image, we can see some molecules are inside the water. So deep inside is not exposed. Some some molecules are on the surface of the liquid with the atmosphere. Okay, so there are two different reactions happening in these two particular region. Okay, one on the surface, one more deep inside. Okay, inside, as we can read here, so it attracts, the molecule attracts equally in all direction by the molecule surrounding it. So meaning one molecule, it will attract all the molecules surrounding it. Okay, but at the surface, you can see what happened. So at the surface between liquid and air, so you have a surface here, surface on top, and you have air on top. Okay, at this surface, what happened? Uh, Upward and downward attraction are unbalanced. So as you can see here, so on top you don't have any attraction, but only inside. Okay, because of this kind of unbalanced attraction, so what it happen? So it's pulling in between the molecule at the surface. Yes, like you can see here, you have two arrows at the sides. So it's pulling the molecule so that it become like a skin. So we call it as a elastic membrane or skin under tension or stretch. Okay, so it's practically it become like a thin layer of protection between the fluid and also the air. Okay, these effects cause the liquid surface to behave as an elastic membrane or skin under tension. Okay, example, a steel needle or a razor blade will float on water if placed gently on the surface because the tension developed by the hypothetical skin supports it. Okay, because of all the skin that is developed. Okay, so it's not something that very visible, but it's there. Okay, it's available there. So when you put a very tiny needle, okay, in Malay we call it jarum. So you put on top of the water gently. So not like with force. You just put very slowly, or the razor blade that you are using, you just place it very without force, okay, softly. So it will float. Okay, it will float. Okay, the surface tension or the coefficient of surface tension is measured as the force acting across the unit length of a line drawn on the in the surface. Practically, we call this as a surface tension. So we are not calling it as a elastic membrane or skin, but there's a name for it. We call it as surface tension. Okay, so it acts as a plane of surface normal to any line of surface and is the same at all points. So meaning you have your your container, so you have fluid inside throughout the surface, so it has the same kind of force acting to make it a surface tension. Okay, so you can see at the table at the side, different fluid has a different surface tension, so measured in Newton meter. Okay. The surface tension is also important at the interface between a liquid, a gas, and solid. Okay, so we can see here, for example, okay, so in between different kind of fluid, okay, like liquid, gas, and or even solid, so we can have a surface different kind of surface tension. So that's what we need to understand. So we can see, uh, I think you are familiar with this meniscus. We call it as meniscus. So meniscus occurs when the surface of a fluid touches solid wall. So meaning you put a container in the water. So what it will make a meniscus. Okay, because a solid container is touching with a liquid. Okay, so as most readily noticed by when a capillary tube is placed in a liquid. So maybe you have conducted this experiment in school. Okay, so what you will do? So you will place a capillary tube inside the water, and you can see the water enters the capillary tube, and it will be having like additional waters or liquid will enter to the capillary, and you will have a height of h. Okay, and you can see the surface will not be straight like this, but it will be curved upward. So if the depends on the density of the liquid. Okay, so consider a glass capillary tube inserted in a liquid such as water. The water will rise up the tube to a height h. So meaning your tube will not go fully in. So there will be a downward force pushing it up, and the liquid will enter it to make it like a fruit. Okay, so it will raise by height h because the surface tension pulls the surface of the water towards the glass. Because it's a glass material, so initially we know there are surface tension on top. So the surface tension will now transfer to this glass material. Okay, so the liquid will enter inside because there will be pull. Okay, the surface tension will pull the surface of the water towards the glass. Okay, the meniscus is the curved surface. So the curved surface, we call it as meniscus. Okay, so we can see different material as different meniscus level. Okay, so you can see, so when you have a water material like water, so it will be like U. The surface will be like U. Okay, and if you connect this line, you can see a certain angle here. So we call it wetting angle. Okay, wetting angle. But for certain material, instead of the surface curve up, it will curve down. So practically, this is like U, and this is like N. Okay, so N and also U. Okay, for this, you can see if you connect this line from the surface, so the angle will be more. Okay, so this material we call this as a wetting fluid. So if it's like U, if it's like N, if we call it as non-wetting fluid. Okay, so if the pi or the angle is less than 90, we call it as wet. So this is less than 90. From the surface to this angle is less than 90. So we call it as wetting fluid. If the angle is more than 90, we call it as non-wetting fluid. Okay, so I have, for example, water wets glass. Okay, so water, so this water, but not wax. So wax, it will have a different kind of angle. So it will be curving down. It's like an N. Okay, so mercury in the other end does not wet a glass. So this mercury you can see in thermometer. Okay, so phenomena of capillary effect can be explained microscopically. Okay, so if you see with microscope what is happening inside, so we can see this kind of thing. So for water, I just try to summarize this. Okay, so you will see uh, there will be a coercive forces. Okay, we have two terms here, coercive force. So coercive force is actually an attractive force that holds molecule of a single substance together. Okay, so whatever molecule with the same substance, so it will try to hold together. And we have another force called adhesive force. So it's actually an attractive force between two particles of different substance. So meaning, so you have a mercury and a glass particles. So it has a adhesive force. Okay, so inside here we will have coercive force inside water, and inside this glass you will have adhesive force. So that's the sim when you simplify that. Okay, so that's what is making the liquid to enter the tube or going down the tube for different material. Okay, so we will enter to the fifth physical property of fluid. So we call it as a vapor pressure. So vapor pressure is very important. Okay, so vapor pressure because when we are dealing with fluid. So it can be whether it is a liquid or whether it's a gas, you will deal with vapor pressure because whatever material that you have, it can vaporize. So it in Malay we call mendidih, okay, ataupun meruap. So all these words are related to vapor pressure. Okay, so we will see some explanation here. So the pressure, okay, pressure we normally call it as a absolute pressure. Okay, at which a liquid will boil is called the vapor pressure. So even you have water, you have a boiling temperature. So the boiling temperature is actually related to pressure. Okay, the pressure is a function of temperature. So meaning whenever the temperature rise or decrease, so there will be pressure involved at the back of it. So something that you cannot see, but there will be pressure build up or pressure reduction. Okay, so vapor pressure increases with temperature. Okay, so that's what we need to understand. In this context, we usually think about the temperature at which boiling occurs. Okay, so we at the naked eyes, we always will relate. Okay, when the temperature achieve 100, so it will start to boil. Okay, but actually there will be a different condition. Okay, you can see here example here. Water boils at 100 degrees Celsius at sea level atmospheric pressure. So now the normal atmospheric pressure that we are having now, we call it as a atmospheric pressure. So so normally the value will be 1 atmospheric pressure. So or 1 atm, absolute atm. Okay. However, in terms of vapor pressure, so initially we saw temperature and pressure, it is interlinked. So you cannot have temperature without pressure, or you cannot have pressure without temperature. Okay, you can be related. Okay, so if we see in terms of vapor pressure, what we can see, what we can say that by increasing the temperature at of water at sea level to 100 degrees Celsius, we increase the vapor pressure to the point at which it is equals to atmospheric pressure 1 atm absolute. So the boiling occurs. Okay. So maybe for a science point of view, we always will explain that water will boil at 100 degrees Celsius, but that is actually something that very weak, something that is not, I won't say is very true. Okay, why? Because that is actually related to the pressure, not the temperature. Okay, because what is actually happening, we can see that's what this term is explaining. So if we can increase the temperature to 100 degrees Celsius and we can make it more than vapor pressure, more than the atmospheric pressure of 1 atm, the boiling will start to occur. So it is easy to visualize that boiling can also occur in water at temperature much below the 100 degrees Celsius if the pressure in the water is reduced to its vapor pressure. So meaning initially we saw this line, so this is at sea level. Sea level is 1 atm. So maybe at the other, maybe on top of a cliff or mountain. So the pressure will be different. So the pressure will be different. So you do not necessarily must have 100 degrees Celsius to make the water boil. So it can be maybe 80 degrees Celsius, the water will start to boil. So that's what I'm trying to make you understand that the boiling of water is not only related to temperature, but is also with pressure. When the temperature is achieving 100 degrees Celsius and the pressure is reduced to the vapor pressure, or meaning the absolute pressure, the water will start to boil. Okay, so it all depends on the vapor pressure. Okay, for example, the vapor pressure of water at 10 degrees Celsius is 0.01 atm. Okay, so this is a they gave a example. So let's say the vapor pressure of water at 10 degrees Celsius is 0.01 atm. Therefore, if the absolute pressure within the water at the temperature is reduced to that values, the water boils. Okay, meaning even at 10 degrees Celsius, the water can boil. So the condition is you need to reduce the temperature or the pressure of the container. So let's say you're eating up something. in a container. So in a container, you are trying to eat up 10 degrees Celsius water. So if you manage to control the pressure to 0.01 or lower, the water will start to boil at 10 degrees Celsius. So that's what we need to understand. Such boiling often occurs in flowing fluid. Okay, especially when the fluid is flowing from one place to another place, this kind of boiling can happen when there are some pressure drop. Okay, so such as on the suction inlet side. Okay, this is in the application. So impeller, you have an impeller like a fan, okay, underwater. So when the fluid is flowing, boiling can happen because there will be a different point underwater or in the flowing fluid, they can have a pressure drop. Okay, so when such boiling does occur in the flowing fluid, the vapor bubbles start growing in local region of very low pressure. Okay, so if you have a flowing fluid, so fluid moving from one place to another place, maybe inside a pipe. So when suddenly you have a very low pressure, so what will it will generate? It will start to generate vapor bubbles inside the water because of the low pressure. So it occurs because there is not enough pressure at the suction end of the pump. So because the sudden pressure drop, so it start to produce water bubble, and this phenomenon we call it as cavitation. Okay, cavitation. Okay, so what is cavitation? Cavitation is not desirable for several reasons. So cavitation is actually something very bad when it happens because it has a few side effects. The first, it will start to cause noise. It cause noise because when the bubbles started to come inside the water, then it will start to create a very unpleasant noise. And as the cavitation bubble collapse when they migrate into region with high pressure, because when the water is passing through to a lower pressure, bubble happen. When it goes to a higher pressure again, it will start to break up, and it will start to create a lot of noise. So imagine you have a water pipe, the water pipe, then you suddenly have a air bubble inside, you can suddenly you feel the pipe is making some noise. So that is what we call as cavitation. Okay, second, it can lead to efficiency and reduction of heat transfer in pumps and turbines. So what actually will happen, especially when you have a very viscous, so that's why we always say, uh, after 3 months or after certain kilometer you drive your car, change your engine oil. Because the engine oil will become inefficient, and it don't do it's not, it become like less capable to do heat transfer. Okay, so the same thing can happen in pumps and also turbines, or we call it as turbo machine, especially in underwater. Okay, underwater. And finally, the collapse of these cavitation bubbles cause pitting and corrosion of blades. Okay, and other surface nearby. So it will physically damage all your fans, your propeller or blades. Okay, so it is very undesirable because the industrial kind of blades and also impeller or propeller, so it will be very expensive, especially inside a big ship. So it's very undesirable. So you can see here, this is in normal water. So bubbles cannot form since the vapor pressure is less than atmospheric pressure. So when the vapor pressure is less than atmospheric pressure, bubble will not happen. But when the atmospheric pressure suddenly drop and vapor pressure is more, it will start to produce small bubbles like this. Bubbles can form and rise since the vapor pressure can overcome atmospheric pressure. So it will cause a lot of damage. Okay, so you can see here. So cavitation bubble imploding. So there's a term called imploding. close to a fixed surface, generating a jet, number 4, of the surrounding liquid. So you have a surrounding liquid here, and you have a bubble 1, 2, 3, 4. Okay, so this is the first bubble. So when the pressure started to increase back, what will happen? It will started to have a pressure pressing the bubble, and it will become like number 3, and it start to become 2 or 3. So it will start to separate, and it will cause a lot of things. And especially when you have like a hydraulic application, so it will make your equipment faulty. Okay, so you need to do a lot of maintenance or change to new parts. Okay, so you can see here, so saturation or vapor pressure of water at various temperature. So at different temperature, you can see the saturation pressure will differ. So meaning this is the minimum pressure or the saturation pressure for water at different temperature. Okay, so you can see some of the damages. So, okay, you can see the damages on the blade. So it will become like this. So you can see the water bubble become too hot, and it will start to make the material corrode. So or it will happen. So this is what we call as cavitating propeller. So propeller become like a spring, and it when it become like this, it will become unuseful. So you cannot use it for moving forward over it. So because the it already became like a spring, because it's keep on rotating, uh, so it can't push you forward. It can't create the force for a sheep or whatever to move in front. So these are the damages. So in this case, you need to find a replacement. You need to replace this thing. You cannot use this anymore. So it will increase your cost. Okay. So that's the fifth property, physical property, and we enter to the sixth property, compressibility. So compressibility, I think from the term, how much you can compress something. Okay, so we measure this. Okay, we read first. All fluid are compressible under the application of external force. So whatever force that you have, whatever fluid that you have, when you apply an external force, or maybe you use your hand to push, okay, so it will become compressed. Okay, but depends on the material also. Okay, normally fluid you still can compress a bit. Okay, but solid you cannot. Okay, then it will deform. Okay, the compressibility of the fluid is expressed by its bulk modulus of elasticity, or we call it as E. So there's a term we call as bulk modulus of elasticity, or E. Okay, so that formula or the unit can be used to calculate how much you can compress a particular fluid. Okay, which is the ratio of the change in unit pressure to the corresponding volume change per unit volume. Okay, so I think I just go to here. So you can see here a bulk modulus elasticity is a material property characterizing the compressibility of a fluid, how easy a unit of the fluid volume can be changed, decreased when changing the pressure working upon it. So meaning you have a tube here, so you are giving pressure in all sides. You have 6 sides. You are giving pressure, and from this volume become a smaller volume. So that is what we call as compressibility. Okay, so for water at room temperature is approximately 2.2 times 10 to power of 9 Newton meter square. So at okay, while the air at atmospheric pressure, the isentropic bulk modulus of elasticity is approximately 1.4 times 10 to power of 5. So you can see different fluids, okay, air and also water. So it has a different kind of uh, compressibility level in the value of E. Okay, this actually saying that air is typically 4 orders of magnitude more compressible than water. So meaning this value is lesser. So meaning that will be more compressible. So the smaller the value of E, so it shows that it's more compressible. So this is 4 orders. Air is 4 orders more, meaning so this is 10 to power 5, this is 10 to power of 9. 4 orders different. Okay, so meaning air is 4 times more compressible than water. Okay, so we can see for most practical purposes, liquid may be regarded as incompressible. Okay, mostly liquid consider it incompressible because it's already like semi-solid. So you cannot compress much, but air you can compress. But there will be a situation where we call it as water hammer. Okay, water hammer. There are certain cases such as unsteady flow in pipe. Okay, this because of unsteady flow, water hammer will happen. Okay, when the compressibility should be taken into account. Okay, although liquid are incompressible in nature, but there will be certain situation where there will be too much force that make the damages. Okay, damages or make the water compress. So because of the compressibility of liquid, damages will happen. So gas may be also be treated as incompressible if the change in density is very small. So meaning if the density is not changing less than 3%, we consider that particular gas is incompressible. So we will see what is water hammer. So we have the three condition. So valve close. Valve close meaning there's no water flow. Okay, it's all tutup, so it's off. Okay, meaning you have water. So no pressure to open. Okay, so if you have pressure and this is closed, what will happen? This pipe will become big and it will start to have leakage. Okay, because of too much pressure. Okay, but this is a condition where water is still no pressure and you have a valve closed. Then suddenly you open a valve, your valve, so water will start to move from this point to this point, and suddenly you close again without telling anything. Water is flowing, pressure is entering, and there is a water force. Suddenly you close, then what will happen? It will cause a water hammer. Water hammer. So this is the physical water hammer or steam hammer happen in the field. Okay. So I think we have seen the 6 physical properties of fluid. Okay, so with this, we will end this chapter. So will you please answer the questions given. Thank you.